edge designations, CFA Level 1, pre-reading, quantitative methods, learning module 6, basics of hypothesis testing. This is video number 2. We continue onwards, and just a quick reminder of where we are. What we have done thus far is we've looked at the basic process for hypothesis testing. Okay, we looked at doing it the normal way. I'm going to call it the normal way, just for lack of anything that's a little bit more instructive, where we went through the 7 steps of the hypothesis testing. And remember, we mentioned some providers, some designations go for 3 steps in the hypothesis testing process. Some go for 4, some go for 6, some go for 7. I've chosen to go for the full 7. You'll see there's a little bit of duplication, we understand that, but just to give you the full picture then in terms of hypothesis testing. The second way that we looked at was what we call the p-test, which is another way which will give you exactly the same result as the standard hypothesis test, just another way of doing it. And what we did up until this particular point in time is we looked at hypothesis testing on a very simple basis. And remember, what did we do? What was the key part of the process? We really just compared what we call the critical value. The critical value, for the most part, we get from the Z table. Okay, recall numbers like 1.96, 1.645, things like that. That's my critical value versus the t-stat, the t-statistic. I'm just going to write out what the t-statistic is for you guys. Remember, it was x bar minus what the mean over the standard deviation over the root of n, and we compare those two in order to be able to conclude then on our hypothesis test. But all of it was done on a fairly simple, fairly gentle level. What we do now is we expand a little bit to very specific cases, and as we expand our specific cases, what's going to change? Where I get my critical value from, for the most part, and how I calculate my test statistic, because that changes depending on the circumstances. Okay, we start off over here, and let's have a look then at my learning outcome statement. And you can see what it says. It says identify the appropriate test statistic and interpret the results of the hypothesis test concerning what? Now we get our specific cases. The equality of means. Okay, what is the equality of means? And you'll see what I mean with the equality of means. In this particular example, what can you see? I'm no longer dealing with only one example, I'm dealing with 2 means. So over here, it was nice and easy, wasn't it? We only had one mean. What was the mean? And if you go back to our examples that we've used so far, the results of a varsity class, the mean fat content in the margarine, all good things like that. But remembering there was only one mean. When we come over here, we start to see that we've got other tests of 2 means. And look at the hypothesis test for 2 means. So it is the hypothesis is, and this is what I'm looking to reject. And we'll look at an example in a second. I'm looking to reject the hypothesis that mean number 1 is equal to mean number 2. I don't want them to be the same. Okay, and remember, always with a null hypothesis, that is what I'm looking to reject. Everybody comfortable? In favor of the alternative hypothesis that mean number 1 is greater than, equal to, or at least not equal to mean number 2. They are different. I've got 2 means, and for example, if I just take you over here, just to make it a little bit easier to see, okay, by way of example, let's have a look. From a class of science students, a sample size of 36 is drawn. Their mean mark is 62. Okay. Now we have a look over here. From a class of art students, sample size 49, and the mean grade is 59. What am I trying to prove over here? Now here are my 2 means. So my mean number 1 is equal to the results then from the science students. And my mean number 2 is the results from the art students. And what I'm trying to prove over here, that the 2 means are not equal. Now, if I take you back over here, okay, what would I tell you? That's what I'm trying to reject. It. The mean number 1, the marks from the science guys, and mean number 2, the results from the arts class, are not the same. Okay, in other words, the hypothesis, the null says they are the same, but what am I trying to do? I'm trying to reject that. Okay, so you can see how things have changed when we change the case facts a little bit. Okay, hold on to your seats over here, guys. Look at the test statistic. Now you see, we know the test statistic has to change because if I just show you very briefly, what was my test statistic when there was only one mean? It was x bar only less the mean over standard deviation over the root of n. But now I've got two means, so you see what's changed. X bar 1, x bar 2, mean 1, mean 2. Okay, can you see how everything's changed? Okay, unfortunately, yes, we do need to know this one. Okay, that test statistic. Okay, and if we have a look over here, I'm going to just take you down over here to page 24. Here's the example that we use. Okay, it's an example just to, where we compare two means. I've used science and art students. Okay, just to have a quick look. I'm not going to go through the whole example with you. We've done examples on hypothesis testing. I'm just going to show you the differences really as we change some of the case facts. Step 1, state the hypotheses. Okay, and there we go. Okay, there's my null hypotheses, that the mean of 1, the mean of the art students, and the mean of the art, and if I subtract the 2, I should get to an answer of 0. What does it mean if I get to an answer of 0? It means that they're exactly the same. The mean 1, the science guys, the mean 2, the arts students, are then exactly the same. And that's why the difference is equal to 0. But remembering again, I'm trying to reject that in favor of the alternative hypothesis, that when I subtract the one from each other, I don't get, it's not equal to 0. In other words, they are different. Okay. What is my probability distribution and test statistic that I would use over here? Guys, it is no longer the Z. I now move to T values. Remember, T values, we spoke about those earlier. Those are relating to degrees of freedom. Step 3, I specify my level of significance. Most times it'll be 5. Here's my decision rule, because it's, remember guys, and just a bit of revision, when I say not equal to 0 means it could be greater than or less than. Okay, on both sides, I'm working in two tails. It's a two-tail test. It's not greater than 1 only or less than 1 only. It's in both tails. Is everybody comfortable with that? Okay, and remember, whenever I deal with my degrees of freedom or my t-test, I always go what my sample size is, less 1. But here I've got two samples. I've got 36, which are my science students, and 49 my art. Can you see why I go -2? Because now I have two values over there. Okay, two samples that I'm working with. Step 5 was a little bit of a pain over here, guys, because I needed to do this full test statistic over there. When you go through this, guys, just make sure you can do those calculations as you look at those. There's your formula, there's your calculations, and I run all my numbers. You can see it's not an easy, short process. Always keep in mind that when you look at something long like this, you think to yourself, well, remember, in a CFA exam, each multiple choice question is 90 seconds long. How much can they ask you? So just really get an understanding of this. Unlikely to get a long question like this. Here we go. But there is my test statistic of 1.39. Okay. I'm just going to take you back up here. We didn't do it with you, but okay. When we looked over there at the... sorry, just take you back a page. Remember what we said? We said you need to go and look at to get your, remember, always in every single hypothesis test, we always compare what? We compare the critical value to the versus the test statistic. In this particular example, where do I get my critical value from? Remember, the critical value always depends on the type of distribution. In this particular example, the critical value would have been given from the t-tables. Okay, when I looked at the t-tables, guys, just make sure you can do this and are familiar with the t-tables. Are found in learning module 7. Okay, we get to a degrees of freedom of 1.99 on both sides. Why both sides? It's a two-sided test. So what would you tell me? My critical value is 1.99 positive that side and minus 1.99 that side. When I then go and calculate my test statistic, which was quite a process, as you can see, I got an answer of 1.3988. Okay, what would I do now? Remember, we always compare what? My test statistic to my critical values. Where does 1.3988 test statistic fit in? Well, it fits in over there, doesn't it? Versus what? Minus a critical value of 1.99 on the left hand side and plus 1.99 critical value on the right hand side. And then what would we conclude? I'm going to read it to you. I always like to read this verbatim because you can see exactly how we conclude. Since the value of my test statistic 1.3988 is less extreme than the positive critical value, where does it fall in? It doesn't fall into the rejection region, okay, and therefore it's not in the rejection region because the test statistic, in order to be rejected, would need to fall into there or there. Therefore, we fail to reject HO, so I cannot prove anything. And let's just make the conclusion. We can now conclude that the difference in the average marks of the two means science and art students is not significant at the 5% level. I could not prove anything. When would I be able to prove something, guys? Is if the critical value fell into the rejection regions that I've highlighted there in yellow. Okay, and there is a little bit of information. Okay, now we move on a little bit over here. Okay, identify the appropriate test statistic and hypothesis test results, okay, of two normally distributed concerning the means. Because remember, what we're going to be testing throughout hypothesis testing are both means and variances. Here the test is on a mean of two normally distributed populations. Okay, and if you look over here, I'm going to take you straight down to over here. Okay, and there we go. Okay, and there are my, okay, here's my HO again, okay, which is my null hypothesis, okay, and there's my mean of the one, there is my mean of the other, okay, and remember what the null hypothesis is saying is that they are equal, and remember always, guys, that's what I'm trying to reject, okay, I'm trying to reject the fact that they are the same in favor of the hypothesis that the one mean is either greater than or less than the other mean. Okay, here's your test statistic over there. Okay, unfortunately it's a little bit of a an interesting test statistic. I'm just going to read the example together with you to give you a sense of what type of question you can expect and how it differs from what we saw previously. A program that is believed to improve IQ levels has been offered to school children. IQ levels are believed to be normally distributed, so that's a lovely one. A group of 100 children went on the program, and the mean difference between their IQ levels, okay, was found to be 2, standard deviation of 11. And now we need to say, okay, well, we tested the kiddies before they had the program. We tested their IQs before the program, and we're going to test them again afterwards. And when we did, the difference was 2. In other words, the mean difference was 2, standard deviation of 11. Now we now say, well, is this program which we've tried to develop that improves IQ, is it effective? And of course we give a 5% significance. Can you see how this differs a little bit? We're working with a before and an after, but within the same characteristics. Remember what we dealt with before? Okay, before what did we deal with? We dealt with also two means, mean 1 and mean 2, but that was a completely different, because one was science students, one was art students. Here it's the same students, but it's a before and an after picture. That's obviously the difference over here. They look the same a little bit, but you can see the difference over here. State the hypothesis, okay, and we've done that over there. I'm not going to spend much more time, okay. The test statistic, okay, it's a normally distributed, but remember when I'm using paired comparisons, I'm trying to compare one to the other, we always use t-test. T-tests are, okay, degrees of freedom. Level of significance we can specify over there at 5%. State my decision rule, okay. Can you see why this is a greater than test? I'm trying to say that because what am I trying to, why is this a greater than test, guys? Because we had the IQs of the children before the test, and I'm trying to compare that versus the IQs of the children after the test. I want the IQs of the children after the test to be greater than. Can you see that's why I'm in the right tail? It's a single tail test. The entire 5% level of significance goes and sits there in that particular tail. Okay, and if you read off the t-tables, you'll get your critical value to be 1.66. And as per usual, nothing changes. I'm going to be comparing what? Critical value versus my t-statistic. Okay, I run my t-statistic. Okay, there's all the data for you guys. So do take a look at it and make sure you're familiar with everything that is in there. I'm not going to do the calculations with you, but we come out with a t-statistic, okay, of 1.818. When I compare my actual t-statistic of 1.818, there is my t-statistic. There is my critical value. Good news for us, okay, that the t-statistic falls where? Yes, within the rejection region. Okay, let me read you it again. Since the value of the test statistic of 1.818 is more extreme than the critical value of 1.66, the test statistic falls then, yes, into the rejection region. We reject HO at the 5% level of significance, and we can conclude that the program is effective in increasing IQ levels then of the children. And there's a bit of a conclusion for you. And just when you think it was going to couldn't get any crazier, we turn to page 30. Look what we're trying to prove over here. Identify the appropriate test statistic. Again, you can see that's always going to change. Okay, but now I'm dealing not with means anymore, with the variance of a normal distribution and the equality. In other words, are two variances equal? So that they're two separate cases, of course, and you can see that by the 1 and the 2. Let's get going straight away, and let's start off, okay, and see if we can identify the test statistic, okay, and interpret the results for a hypothesis about the variance of a normally distributed population. Okay, and let's have a look over here. Okay, and you can see over here, here's my hypotheses. We'll do an example with you. HO, you can see we've now moved away. What's the difference over here? We've moved away from means. We're now dealing with variances. Okay, the minute you deal with variances, what changes? We move away from Z tables to chi-square tables with an n-1 level of degrees of freedom. My test statistic moves to that. And guys, I'm just going to show you the differences. I wouldn't focus too deeply on these. Just get an understanding of what is going on over here. Okay, and there is, remember over here, what's changed? Two things have changed. My t-statistic, of course, will change, as well as my critical value. I no longer use t-value, z tables or t-tables. Okay, but I use a chi-square graph. That looks like that. Okay. And remember, we have spoken about chi-tests already when we looked at them in the distributions section. Okay. And let's have a quick just look at the examples just to make sure we are familiar with what they like to ask. In the past, documentation about a certain share has indicated that its price is not that volatile. Now, what's volatile? We normally measure volatility by things like standard deviation and variances. And it has a variance of 25. A market analyst comes along and says, no, this share is much more volatile than that, and he wants to test this. So what does he do? He collects share prices over a 25-day period, and he sees, no, look over here. The variance is 36. Now, what would you say straight away? That a variance of 36, which will obviously translate into a standard deviation once you root it, versus a variance of 25, the variance of 36 is way more volatile. So he kind of like has proven his point, but by now we know that what? We don't prove points like that. What do we have to do? We have to then go and say, okay, let's do our hypothesis testing. And he wants to test the claim at a 5% level of significance. Same story. Look over here. State the hypothesis. The null hypothesis says that the variance is equal to 25. We want to reject that. We say it's no. It is not so low. It's more volatile than that. And we say, and we want to reject that in favor of accepting the fact that what? that the variance is greater than 25. So what did you tell me? Oh, okay, we know where we are now. Identify the test statistic. The test statistic, it's going to be a chi-square test. Okay, significance level 5%. What's my state? My decision rule. My decision rule is I'm going to be working over there. I go read off the 5% on the chi-square table, and I get my critical value of 30.14. Okay, I go then, as we know, and I do my step 5. Okay, and I calculate all my data. When I calculate my data, that means I'm going to be calculating my test statistic to compare to the critical value of 30.14, which, by the way, I read off from the chi-square tables. Okay, what do I get when I run my t statistics? I get 27.36, and again, so there is my 30.14, which 30.14 was what? 30.14 was my critical value from where? From the chi-square tables, versus my test statistic over there. Okay, unfortunately, since the value of the test statistic is 27.36, is not sitting in there in the rejection region, the test statistic falls into the acceptance region. We would love it to fall into the our section over there, the rejection region. We would not reject it at a 5% level. Let's make our conclusion. We can conclude that there is not enough evidence at least at the 5% level of significance that the variance of the share price is greater than 25. We continue on with the next case, and unfortunately they do get a little bit more complex then as we move forward. And the next example again deals with variances, but now it's the variances of two normally distributed populations based on two independent random samples. So as you can see, as we move forward down the process, okay, the cases just get a little bit more complicated. Again, just remembering again here we are dealing with variances, equality of variances, so you can see there will be two. If we look over here, what is my HO? What is my null hypothesis? That variance 1 is equal to variance 2. They are equal, and that's obviously what we are trying to reject in favor of the alternative hypothesis, in saying that no, variance 1 is greater than or equal to variance 2. Okay, and that's what we are trying to accept. We use the F statistic over here. F stands for Fisher. The F statistic, not so crazy. I'm sure you're quite relieved. There is your F statistic, S1 over S2. Nothing too crazy. Again, we use the F statistic with n-1 and n2-1 degrees of freedom. On our page over here, okay, there is what your graph looks like. Fun. There is your F graph. Remember, again, it is truncated at 0. We've seen that before when we looked at distributions. Okay, let's have a quick look at an example of what we can expect in such a case. Okay, a university administrator wishes to compare the divergence, the difference of grades in the year-end exams of its actuarial science students and its commerce students. In order to do so, he collects a sample of 41 actuarial marks, 31 commerce marks, and what did he find? A standard deviation of 10 and 8 respectively in the two different marks. Okay, the year-end grades are normally distributed, and we are going to be using a level of significance of 0.10 or 10%. Let's have a quick look. State the hypotheses. Okay, is, and this is what we're trying to reject, that the variance of the actuarial students and the variance of the commerce students is equal. We're saying no, we want to reject the fact that and say they are not equal in favor of the alternative, that they are different. In other words, not equal to 0. As per usual, step 2, what is the test statistic and its probability distribution? F test, okay, level of significance, we identify as 10%. Okay, we go and state the decision rule, and for that we're going to go and look on our table. Remember, every single test doesn't change. I wish it would change. It gets a little bit boring, but hey, at least it's consistent. It's critical value versus test statistic. Where we get the critical value, that of course will change. I get here mine from my F table, and I get to a critical value of 1.79 when I read off the table. There we go. Okay, step 5 is when I now go and calculate my t statistic. Okay, and I get to 1.5625. Remember this F value or your t value, we know it's still a t statistic, but we're just going to call it the F value because that's where it's derived from, is 1.56. So again, 1.56 is my F stat stroke F value, call it whatever you like, versus my critical value, okay, of 1.79, keeping in mind, of course, that then would be the rejection region. That's where I do want to be. And since the value of the test statistic at 1.56, okay, is less extreme than the critical value, unfortunately, the test statistic does not fall in the rejection region, but in the acceptance region, and we fail to reject HO, at least at a 10% level of significance. And we can conclude insufficient evidence that at least at the 10% level of significance, there's any kind of divergence in the marks between the various students in our particular case. Guys, that then brings us to a conclusion of hypothesis testing, and I always smile when they call this the basics of hypothesis testing. I know it does get a bit more complicated, but I'm sure I'm sure everybody appreciates that we did go quite deep into hypothesis testing. And there we go. Page 38, we've got a summary over there. 38, 39 does go on a little bit, giving you all the various numbers that we need. Okay, and just remember, of course, we look at the various tests, and what keeps changing, guys, is what table we use. Z, T, chi-squared, F table. It'll all depend on what kind of a distribution we're dealing with, and then, of course, how we calculate our T statistic. As per usual, guys, we go back to the beginning of the learning module as we normally do, and I always just ask of you, just when you are done with a particular learning module, go back to the beginning and just have a look and make sure that you are able to identify and work with a particular learning outcome statement. Just go through them again. For example, there, compare and contrast a one-tailed versus a two-tailed test. Do you know what that means? Can you explain that? If yes, okay, then you've got the basics of what was in the learning module. If not, then it's still a little bit unclear to you as you go through the various learning outcome statements. Perhaps one should go through them a second time. Good news is that then brings us to a conclusion of the pre-reading for quantitative methods. Remember, guys, that's learning module 6. Learning module 7 is really just the quantitative tables. So good news, those that are at this point together with us have now completed the pre-readings for quantitative methods, and are hopefully in a fantastic position then to move on to the quantitative methods core readings.